Hi, Dr. Lyons here. Today I'm going to record a lecture for my engineering materials class, and the topic of the lecture is deformation mechanisms. In this lecture we are going to discuss deformation mechanisms. Deformation mechanisms. In other words, at an atomic and crystal level, how do metals deform? How do the atoms rearrange themselves under stress? First, we'll talk about elastic deformation. In elastic deformation, the mechanism of deformation is the stretching of atomic bonds. The mechanism is the stretching of atomic bonds. So if we have two atoms, then separated by some distance A, and we apply a force, the atoms will move farther apart. And when we remove that force, they will come back together. If you will recall from Chapter 2 of the Shackelford textbook, the forces between the atoms is made up of a Coulombic attractive force. Fc is the attractive force. Fr is a repulsive force. And the net force is F, which is just the sum of the Coulombic attractive force plus the repulsive force. In Chapter 2, there was a picture, figure 2.7. That's hard to read that, so I'm going to redraw it here. Force versus position A. And I'm going to draw a dotted line about 1/3 of the way out on the A-axis. So the attractive force increases as the atoms get closer together, and it decreases as the spacing increases. So our attractive force curve looks something like that. The repulsive force becomes greater in a repulsive sense or in a negative sense as we push the atoms together. So we have a curve that looks like that for the repulsive force, and when you add these two together, you get a curve that's shaped kind of like that, which is the net force. So right around here where the force is 0 is our equilibrium distance. And right there the slope of the FA curve is delta F over delta A at the equilibrium position A0. And M is proportional to the elastic modulus. M is proportional to the elastic modulus. So that's pretty simple. Things, the stretch, you can almost think of the elastic deformation acting like a spring between two spheres, where if we pull them apart, the spring wants to pull them back together. As we compress the spring, the resistance increases until we get to a point where the two spheres are actually touching, at which case the force becomes infinitely large to move them any closer together, which is why this curve drops sort of asymptotically. things I think are a little more interesting when we talk about plastic deformation. Section 2 is plastic deformation. And the mechanism of plastic deformation in metals is dislocation slip. Dislocation slip. Now it's kind of a weird thing to understand, so I'm going to give a macro analogy. And I'm going to talk about a rain tarp. So I was at a minor league baseball game, and it started to rain. And some dudes came out with a big piece of plastic to cover up the field. And here's the field, and let's say this is third base. And what they did was when they rolled the tarp out, they didn't cover third base. So there was this, it didn't make it all the way there. So this is the tarp, and this is the ground. And so this dude was standing there pulling as hard as he could and could not get that tarp to move because it was touching the ground all along here. And it was raining. And the more it rained, the heavier the tarp got, and the more futile it seemed for this dude to be able to pull the entire tarp and have it slide along the ground. Well, somebody who was smart came out and introduced a dislocation. And there's third base. And what they did was they picked up this end of the tarp. And they were able to just push that dislocation, or that, so they were able to just push that dislocation along the length of the tarp. So what they did here was they introduced and moved a dislocation. So a little while later, as he was pushing it along, let's see, let me get this right. So this is where this started. So a little while later, after we introduced the dislocation, that end of the tarp had moved. There was the dislocation, still hadn't reached the end yet. And eventually, the dislocation was moved all the way to the end, at which point it popped out. And we were able to cover up the baseline from third base to home plate. So I saw that, I was like, wow, I ought to talk about that in my class, because that is an excellent example of why and how metals deform by dislocation motion. And it was actually theorized in the 1930s that these dislocations existed and led to deformation of metals. So the folks in the 1930s were doing calculations on crystal strengths, and they observed that the yield strength in actuality was much less than the yield strength in theory based on the atomic bond strength. And the reason why is that instead of shearing a whole plane of atoms, instead of shearing a whole plane of atoms, or atom bonds, simultaneously, Motion of a dislocation only shears the bonds along the dislocation line. Motion of a dislocation shears only the bonds along the dislocation line. So let's see what the textbook looks like on that. Okay, so here is figure 620. So I can zoom in a little bit. And here's a simple cubic crystal structure and if I apply a shear stress, moving the top part to the right and the bottom part to the left, I can introduce a dislocation by breaking the bond between just two of those atoms, or actually, it's all the atoms in that plane going into the book, into the surface of the page. So once I have that dislocation, that atom will connect to that atom, and that atom bond between those two will break, as we've seen in this picture. So now the dislocation has moved one step to the right, and this process will repeat where the bond between those two atoms will break. Here we'll have a reformation between that atom and that atom, leaving that line of the dislocations being free. So we've got right that, and so this process keeps walking itself through until we have stepped a one atom distance off of the other surface of the crystal, or of the grain if it's on the grain boundary scale. So that's how dislocations will move through the material under a shear stress. So the mechanism of plastic deformation in metals is called dislocation slip. Slip is the process where the dislocation walks through the sample. Now, one of the things to recall from our previous discussions is that the dislocations cause lattice distortions. Dislocations cause lattice distortions. And for an edge dislocation, these are compressive above the slip plane. Compressive above the slip plane. And tensile below the slip plane. In a screw dislocation, these distortions are pure shear. Screw has pure shear distortions. Now, the result of this is that the dislocation slip is easiest on planes and directions where this lattice distortion is minimized. Dislocation slip is easiest on planes and in directions where lattice distortion is minimized. These are the closed packed planes and directions. Planes with the highest planar density and linear density. So we're going to talk about slip systems, slip in single crystals, and slip in polycrystals. Slip systems. Slip systems are made up of a slip plane plus slip directions. The slip plane is the plane given by Miller indices HKL with the highest planar density. PD is planar density if you don't remember that. And slip directions are the directions given by Miller indices HKL with the highest LD, or linear density. So in this chapter and elsewhere, we are going to use the concept of a family of planes as a shorthand notation. So when I put 3 Miller indices in parentheses like that, which I think are called braces, that includes all of the 1, 1, 1 type planes. So 1, 1, 1, negative 1, 1, negative 1, 1, 1, 3 negatives, etc. These are all equivalent planes. In that they have the same shape, they have the same shape and planar density. Similarly, we will have a family of directions, which we use these angled parentheses for. And for example, 1, negative 1, 0 includes all of the directions 1, 1 bar 0, 1, 1, 0, 0, 1, negative 1, etc. All the combinations of zeros and 2 1s or negative 1s. These all have the same linear density. So, for example, a slip system family for FCC is the combinations of planes that are 1, 1, 1 planes and directions which are 1, negative 1, 0 directions. Okay, so how many of those exist within a given crystal? Well, let's see. If we've got a unit cell, then this thing that I'm drawing right here is a 1, 1, 1 plane. And it has, so that is a 1, 1, 1 type plane. And there are 3 1 bar 0 type directions on that plane. Where are they? So that's the edges of the plane or the diagonal of the face of the cube. Okay, so there are 3 slip directions per slip plane. How many slip planes are there? What is the number of slip planes? Well, let's think about this just from inspection. That's one of them. There's a cube. Another one we'll just work our way around from that corner to that corner. It's hard to see that the way I've got that drawn, isn't it? And then if I draw another one here, start from this top corner, go to those 2 corners there. And then we got one more to draw at that back corner. So another cube, starting there, with those 3 points as the intersects, is the corners of that triangle. So therefore there's 4 slip planes that are not parallel. So as a result of having 4 planes, each with 3 directions, there are 12 what we consider independent slip systems in FCC. So here is table 6.8 in the book, and we're looking at here at the FCC. There's the 1-1-1 slip planes, the 1 bar 1 0 slip directions. 4 planes times 3 directions is 12. Give some examples of some materials which have that many slip systems. Now, in the hexagonal close-packed, the slip plane is the base plane, 0, 0, 0, 1. And the directions are the edges of the hexagons, which are 1, 1, 2 bar 0. Now, there is a top plane and a bottom plane, but those are parallel, so there's really only one slip plane in HCCP, each with 3 non-parallel directions. So that means there's only a total of 3 slip systems in HCP. So the thing to note is that HCP crystals have few slip systems, just 3. And because of that, you don't get, therefore, dislocation motion doesn't have a lot of direction that it can go in, and because there's not very many slip systems, HCPs are generally brittle materials. And it all has to do with their the number of slip systems in the unit cell. All right, so we'll talk a little bit more now about slip in single crystals. Okay, so recall that slip results from shear stresses on a slip plane in a slip direction. Slip results from shear stresses, tau, on a slip plane in a slip direction. So here's figure 627 from the Shackelford textbook, showing a tensile test bar on a single crystal where all of the atoms are in the same atomic arrangement and orientation. Force is being applied. Let's say the 111 direction happens, or the 111 plane happens to be as shown in that orientation. So that is the slip plane, and then the slip direction is as indicated right there. So we've got a shear stress that's acting on the slip plane and in the slip direction. Now, if you'll remember from your solid mechanics, this shear stress is going to be a maximum on 45 degrees to the, it's not going to be a maximum on 45, it's going to be a maximum on a plane and in a direction that's 45 degrees to the applied normal stress. But here we're talking about resolving the shear stress on a specific plane that's defined by the crystal orientation. So if phi is the angle between the normal to the slip plane and the tensile axis, phi is the angle between the slip plane and normal, So if we're trying to figure out what the stress is on that plane, we're trying to find the resolved shear stress. That is going for a particular slip system. So that's tau r, and that is the component of the force that's causing the shear divided by the area of the shear plane. Okay, so here is the end of my single crystal tensile specimen. Force is applied. I'm going to have the slip direction in some angle off to the right. And the angle between the normal force and the slip direction, which is the direction we're trying to find tau r in, is lambda. Lambda is the angle between the slip direction and the tensile axis. Okay, so F shear is going to be F times cosine lambda. Now, the cross-sectional area we can get from the orientation of the slip plane with respect to the tensile axis, and we'll say phi is the angle between the normal to the slip plane. That's the normal direction. Phi is the angle between the normal to the slip plane and the tensile axis. And under that situation, then the shear plane area is the total cross-sectional area over cosine phi. A is the sample cross-section. So we substitute A shear and F shear into the definition for tau r, and we get F over A times cosine lambda times cosine V, or just normal stress times cosine lambda cosine phi. And that, I'm sorry, is resolved shear stress tau r. So in a given crystal, the slip is going to occur first on a slip system with the highest value of cosine lambda cosine phi. Therefore, slip occurs first on a system with the highest value of the quantity cosine lambda times cosine phi. And the language that we use to describe that is we say that system is the most favorably oriented. Most favorably oriented. So that's the applied stress. The material property is called the critical resolved shear stress. So this is can be considered a material property. And it results when yielding occurs. And yielding occurs when the resolved shear stress reaches or exceeds the critical resolved shear stress. And that is the critical resolved shear stress. So if we solve for the yield strength from the previous equation with the cosine lambda and cosine phi, I get the yield strength is the tau CRSS divided by cosine phi cosine gamma max. So in a single crystal, the yield strength depends on the crystal's orientation. It depends on lambda and phi. So the yield strength of a single crystal depends on its crystal orientation. Which is pretty cool. Okay, so now let's talk about polycrystals, which are materials made up of many crystals, which are most commercially available, structural metals, and so on. So number 3 is dislocation, slip in polycrystals. Polycrystals are materials made of grains with grain boundaries between them. So let's say that the grains have random crystal orientations. I'm going to put random in quotes because that is something that can be controlled by processing a little bit. Well, if that happens, then slip occurs on a zigzag path. Slip occurs on what I call a zigzag path. But the average direction, or the average slip path, is the plane with the maximum applied shear stress. So if you will remember a little bit of a previous course called Design, where you talked about Moore's circle, that was a plot of normal stress versus shear stress. And for a simple tension, we've got sigma 1, sigma 2 is 0. Maximum shear stress occurs when that angle to theta is equal to 90 degrees. So therefore the maximum shear stress occurs on a theta equals 45 degree plane. So how does that relate to this zigzag path? Well, if I've got a sample being stretched, and it's made up of different grains, and I'm drawing the grain boundaries here between them, and let's say this grain has its slip system oriented like that. This one has its orientation like that. Maybe this one is like that, and we'll put this one somehow like that. Then what's going to happen is that the slip is going to generally occur at an angle of 45 degrees to the tensile axis. But on a local level, the dislocation motion is following the crystallographic plane orientation. And the properties of the bulk material are going to be some average of the properties of the deformation of each. So the properties of the bulk material are going to be a function of the material property, the critical resolved shear stress, for example, of the individual grain, and how those grains are oriented within the crystal. So that ends the lecture on deformation mechanisms in metals, and thank you for watching.